Hello everyone, welcome to our math presentation, brought to you by myself Radi, Andreas, Changler, and Herzan. So this is the question. A tank shaped like a vertical cylinder initially contains water to a depth of 9 meters. The bottom plug is pulled at the time of t is equal to 0. After an hour, the depth has dropped to 4 meters. Determine how long it would take for all of the water to drain from the tank if the rate of the change of depth of water in the cylinder y is described as dy over dt is equal to negative k square root y, where y is the depth of water in the cylinder, t is the time in terms of hours, and k is the constant. The differential equation in the above can be derived using the Bernoulli equation and mass continuity equation. The Bernoulli equation is the Bernoulli equation is pressure over density plus 0.5 v square plus gz is equal to 0. And the mass continuity equation is mass in minus mass out plus generation minus consumption is equal to accumulation. So the question is, derive the differential equation of dy over dt is equal to k square root y and express k in terms of properties of the system. This is a visualization of the information given in the question. We know that V1 is equal to 0 because the rate of water going down is negligible. P1 and P2 are assumed to be atmospheric pressure, whereas for V2, we shall label it as V. And to get the height and to get the change in height, we'll take Z2 minus Z1. So this is what it looks like when the cylinder is full. And after the plug is pulled, the cylinder is drained after an hour and the water level drops to 4 meters. So we have to find the amount of time it takes for the cylinder to be fully drained, which is dt. Now I have Andreas to talk about the application for the Bernoulli equation.
Now, application of Bernoulli equation. Firstly, the formula of Bernoulli equation is pressure divided by density plus 0.5 times velocity plus gravity times height. In order to solve the Bernoulli equation, we have to know pressure, velocity, and height. We have gravity and density as both are constant. Pressure will be atmospheric pressure, and P1 equals to P2 as the container is not tall enough to have varying pressure. For velocity, we can equate V1 equals to 0 as the water level decreasing is at a very slow rate. Hence, V2 equals to V, since V1 is negligible. For height, we take Z1, which is the height at the top cylinder, minus Z2, which is the height of the water as it decreases, to get Y, which is height in the formula. Since we know that water has a density of 1 kg per meter cube and gravity is 9.8 meter per second square, we can solve the equation. After putting everything into the formula and solving and factorizing it, we get V equals to squared 2gy.
Now moving on to the mass continuity equation, it is stated that mass in minus mass out plus generation minus consumption and is equals to accumulation. So from the diagram, it is proven that mass in is equals to 0 because there is no active water input. Thus, mass in is equals to 0. Mass out is derived as velocity multiplied by area multiplied by the rate of change of time, which is dt. Generation and consumption is equals to 0 because there is no reaction taking place in the apparatus. There is no consumption of reactants and generation of the products. Thus, consumption and generation is equals to 0. There is only decrease in volume, which means that no water is going in and only water is going out. Thus, from that we can deduce that the rate of change of volume, negative dV, is equals to accumulation.
Okay, so from both Bernoulli equation and the mass continuity equation, we now know that 0, which is the mass in, minus mass out, plus generation, which is also 0, minus consumption, which is also 0, is equal to the rate of change of volume. And we also know that mass out is velocity times area times the rate of change of time, which is 2 square root 2 gy times pi r2 square times dt equals to minus dv. And we will simplify it to have dv equals to square root 2 gy times pi times r's 2 square times dt, which would then be our equation 1. Next, we have the volume of the cylinder, which is pi r1 square times y, which is the height of the cylinder. And change in volume would just be dv equals to pi r1 square times dy. And that will be our equation 2. Now, we'll sub equation 1 into equation 2. And then we will have pi r1 square dy equals to square root 2 gy pi r2 square dt. And we'll rearrange it to have dy over dt equals to square root 2 gy times pi r2 square over pi r1 square. And we further simplify it to get dy over dt equals to r2 square over r1 square times square root 2g times square root y. And by comparing coefficients with the initial equation, we have dy over dt equals to minus k square root y. And we will therefore get minus k equals to r2 square over r1 square times 2g. And k would then be negative k would equal to negative r2 square over r1 square times 2g. And that is how you express k in terms of the given parameters and how we derive the initial equation from using the Bernoulli equation and the mass continuity equation. And that is all. Thank you for watching our video. Please give us A+.
All right.
Right.
Hey, Chandler,
What?
edit out the